Welcome to Unit 9 on services and enclosures. This unit we will talk about a lot of different configurations that service connections can be installed in, such as overhead and underground. We'll talk about clearances of that overhead conductor. Then we'll also look at the electrical services requirement for Southern California Edison as an example of what utilities will require when installing services. So the electrical utility needs to spec the location and it needs to be installed according to their specifications. And it is either the same as the National Electrical Code or more stringent than the National Electrical Code. So it never will be less than the NEC. So I wanted to at least expose you to that. You may work in other utilities as you're connecting services down the road, but at least you'll have an understanding of what Southern California Edison's electrical service requirements look like, and then be able to know how, or at least know you need to contact the serving utility for their electrical service requirements. Then at the very end, we're going to introduce grounding at services. So grounding will be sprinkled throughout a few of the sections here, and then we will also talk about grounding again very specifically and grounding related issues at the towards the end of the class in the later modules. So go ahead and grab your book and open it up so we can go into it. So we're going to talk about the service entrance wiring methods and the different ways that we can bring conductor from the utility to the service location. And there's been many different options, especially when you go state to state and utility to utility or co-ops, whoever's providing the power to the property will allow different types of installations. And so I'm going to focus primarily on West Coast, where you will probably be working the most if you're going to deal with installing services or upgrading services. There are a lot of different options for connecting to different utilities, different methods. So I'm going to kind of steer away from those as we go through. And after we're done talking about the wiring methods for services, we'll go and look at the electrical service requirements for Southern California Edison, again, just to give you some exposure to what that would look like. When we talk about the service mast as support, we're looking at the service entrance and overhead service conductors shall be arranged so that water shall not enter the raceway or equipment. So we have to have a weatherhead on top. Now, the way this is designed is you would buy a 1 to 2 sections of the galvanized rigid conduit, and you're going to use the threaded end in a hub that then screws to the top of the panel. And then you're going to cut this end to be the height that you need and just cut it off. And then this weatherhead will then clamp on to that cut piece of pipe. Make sure, of course, it's reamed, but you don't need to thread the top of it, which is very helpful when we're trying to install in the field, especially residential construction. The other is we need to look at that it is not required, where approved, that rigid or intermediate conduit be securely fastened within 3 feet of the service head or for above the roof termination of the mast. Now, we need to make sure that we do secure it, and that the upper secured point inside a wall, so the top cap of the wall, if it's internal, is considered a secure attachment point to help the mast from not pulling over. So you got to think about this weight of this triplex overhead conductor, which is primarily used now. And triplex is a bare steel neutral, and then an insulated two hots. So the supporting wire, the guy wire, is the neutral, and then the two insulated are wrapped around. We call that triplex, 3 wires wrapped together. There's a considerable weight to that depending on the distance it has to go. So we have to think about what's this conduit going to do? And so using galvanized rigid conduit is going to be the best option. And I would stick with using the best option. Cost-wise, this is not much different with IMC type conduit or intermediate rigid conduit. So the next thing we want to look at is open conductors must be attached to the fittings identified for use with service conductors or a non-combustible, non-absorbent insulator securely attached to the building or structure. So this is giving us two options. Now the utility is going to also govern that. They may say, no, you cannot attach the triplex to the house or the structure. You need to attach it to the riser, because the riser is going to be stronger in how it's connected. The service must be of adequate length. Service mast must be of adequate length, so that it has the proper braces on there to withstand any type of wind or movement or load from the overhead service drop. So if for some reason you had to be higher here, then you need to provide bracing down to the roof in order to secure that point of attachment. So if this was the mast and the wire is going towards here, then we need to have bracing back this way to hold it from moving this direction, because the weight will want to pull it like that. So you're going to want to make sure you seal it as well. So you're going to have a roof jack that's going to be installed, and then later on a roofer will need to come back and seal it up. I want to make sure that we don't use that service mast for attachment of any other type of service. Telephone, communications, cabling will not connect to it. We also don't want to support the wires from any type of trees. Vegetation cannot be used as a support. We don't use service entrance cable in the West Coast. It's going to be triplex as a standard, so I'm skipping this one, but you can read up on it. For conductors considered outside of the building, our demarcation point, what we would look at is anything coming out of the riser, or which is the mast, or coming from the underground where it penetrates through the slab location. That is considered outside by the code. The utility, however, will control the wiring from the service all the way out to the transformer, and they will control it, but yet you will be required to install it on overhead to come out, but that's all under the control of the utility. Underground services. So what we want to look at here is that we have to look at table 300.5. So in 300.5, this is the minimum cover requirements from 0 to 1,000 volts, nominal, buried, and then inches is millimeters, and then inches is in parentheses. So we got to take a look here, make sure you're looking at the right one. But this table is very important because it gives us the column of the type of conduit or conductor that we're burying, and then we have to look over here for the location on the side here for how then it would be installed. So for example, if it's under a building, all options are 0 inches. It can be directly buried right under the building. The idea is that we're protecting that conduit and we're protecting the conductor, especially if it's UF cable that's laid right in the ground or direct buried. So underneath a slab, it's protected. However, I would go a little deeper, because if they ever saw cut that in the future, you want to make sure you've got some distance between that saw cut. So when we look at all locations not specified below, so everything not specified, it's going to be 24 inches for direct buried cable. For rigid metal conduit and intermediate conduit, it goes to 6. So let's say that you can't get lower than 12 inches, and you need to get you need to get to that depth of 12 inches, or actually below that. You may have to go from direct buried and put it into conduit. And we see that over here we could do residential branch circuits rated at 120 volts or less with GFI protection. Maximum overload current of 20 amps can be as shallow as 6 inches, but in this case where it's not covered below, it would be 12. So we have to use this to interpret. Now, if we go underneath streets, highways, roads, alleys, driveways, and parking lots, driveways, you can have that in residential. And we're looking at 24 inches across the board. Doesn't matter what we use, it needs to be 24 inches down. Part of this is, especially on highways, it may be even deeper because highway road bed is sometimes more than 24 inches deep. So when they're going to redo it or work on it, they don't want to be hitting conduit. Now, a 1 to 2 family dwelling and driveways and outdoor parking areas, or used for the dwelling related purposes. So we're not parking semi trucks or heavy equipment on here. And we can go to 18 inches. And then in most cases here. So in this column 3, non-metallic raceway, that's PVC conduit. So you have PVC, you have metal, and you have direct buried. And that will give you a better understanding of the depth that you're looking at. So again, table 300.5. So with our service entrance conductors, we do have to meet that table 300.5. But we want to look, and we have to look at the electrical service requirements of the serving utilities to find out what size conduit this may be. There may be a minimum 3-inch size in the ESR requirements for that utility that have to be abided by. And so you can't just run any conduit out there. You need to work with the utility to find out what the size is. And of course, we know that a 200 amp panel, and we size the conduit, it's not going to be 3-inch. But 3-inch gives the opportunity to go with the largest conductor. And frankly, the utility will make it easier for them to pull it, and they would like a larger conduit. So we have to accommodate for that. In the case of having to use underground service cable, where it can be direct buried, you can use a conduit that just 90s out and heads the direction that you need to run. And you have to make sure that it is protected with a bushing, and then the direct buried cable can go right out into the earth at that point. In the 1980s, 70s, 80s, and early 90s, direct buried cable was used quite often in track home construction and has been moved away from, at least from a utility service perspective. Everything's going to be in conduit because when this fails, it's a lot of money to repair that. Now, I wanted to talk about clearance. Now, think again just about safety. Why are we requiring these types of clearances? What's the reasoning between the distances? Why is it specified to have a minimum of such and such clearance? I want you to keep that in mind as we go through this. Because what we're trying to do ultimately is we want to keep people safe, right? We want to protect persons and property. We don't want a truck hitting it, knocking it down, causing a safety issue. We also don't want to have somebody contacting it or touching it. Let's take a look then at the accessibility to pedestrians. So 10 foot is going to be this requirement, the minimum number. And so the point of attachment of the service conductors to the building must meet 230.9 and 230.24 minimum clearance requirements. And in all cases, this point of attachment must be at least 10 feet above finished grade. So this is the minimum. So we want to make sure that they cannot reach it. Growing up, my dad had set up an above ground pool, and not knowing the requirements, had set it up right underneath an overhead service drop to our house. And he told me to not touch those wires. Well, as a young boy, I realized that if I touched ground and the wires, I could get hurt. But I looked at the birds and saw, well, the birds are sitting on the wires and they're not getting hurt. So, of course, I would jump off the deck and slap the wires and then jump in the pool. So, destined to be an electrician, right? So don't do that. That's why we don't want to have wiring over pool locations. That's in another section. But the idea is we don't want to have any contact. Even though these are insulated, we still don't want to have contact with them. And we look at vertical clearances here, and we're over different types of locations. We're over stairs, minimum 10 feet for pedestrian. And then we have driveway, and we have a going out farther here into the street. So when we look at B says a minimum of 12 foot of vertical clearance required for residential properties and driveways and over commercial areas, not subject to truck traffic, because trucks are taller than 12 feet. And then it says that this voltage does not exceed 300 volts to ground. Now, conductors exceeding 300 volts to ground need a minimum clearance of 15 feet. Okay, so we have 12 feet for residential, and if we're above 300 volts, we need to be 15 feet. And then when we get into streets, alleys, roads, parking areas, subject to truck traffic, driveways, and non-residential properties that or other than land traversed over by vehicles, it is a minimum of 18 feet. Now it says here that such as cultivated, grazing, forest, or orchard, we want to make sure that the equipment can go underneath it. So the higher, the better in many cases. The utility, when they install it, will govern that. But over here, our mast needs to be high enough that we can make sure we meet the requirements on the property. The rest of it is going to be maintained by the utility as they're connecting it to the pole to make sure that they have access. Now, when we look down here at the bottom, when we look at the bottom, we've got a illustration of a window and how you cannot, when you're making an attachment point on the side of the building, you need to be more than 3 feet away in all directions from that window. Why 3 feet? Well, get a measuring tape out and measure the length of your arm, and you would see that you would be at a little less than probably 3 feet. So depending on how big you are or how small you are, will change that. But they don't want you opening the window and reaching out and grabbing the wiring. The non-opening windows permitted to be underneath it. This one here, B is 3 foot clearance is required, does not apply to conductors running above the top level of the window. So if it goes above it, then we don't need to meet the requirements. We can see here in this illustration that it's to the side and down. And then looking down at it, when we also cannot have less than 3 feet of conductor going across the front of the window. So this is not ideal. It'd be better to have this up as high as possible. But you just need to understand that there are these minimum points that we have to watch. So as you look through these, I'm going to let you guys read through these locations. Sloping roofs, flat roofs, various roof designs. These are all specific to the architecture. And if you think about this, you are going to realize that if I'm on a flat roof, I need to make sure I maintain enough clearance so that I can't touch that location, 8 foot minimum in this case, from being on the roof. So I want you to think about, well, you could set a ladder up there. There's a lot of things you can do on a flat roof that you can't do on a pitched roof. But look through these and understand them specifically. Now, the working space around equipment we need to touch on, because this applies not only to residential, but it also applies to commercial. And so in a equipment room or working space around a panel is a minimum of 6 feet. There has to be a minimum of 6 feet of headroom to work on the equipment. So you need to be able to stand in front of the panel and not crouch. And if you're over 6.5 foot, if you're over 6.5 foot, then 6'6", then you're going to have trouble. But this is aimed at the average height of a person so that they can stand in front of this panel and work safely. And we also need to make sure that we have a working space width, and that's what this one over here is. So you just got to remember 30 inches. That 30 inches, even if the panel width is smaller than 30 inches, you need to have 30 inches of clearance on each side from anything conductive. And this comes from 110.26A2. And this can be set up in this configuration where it's 30 inches from one side to the other, or opposite, but it needs to be 30 inches of working space in front of the panel. When we look at the maximum depth, it says here that in the electrical installation, other associated equipment location above or below the electrical equipment shall not extend more than 6 inches beyond the front of the equipment. So if the panel is 6 inches deep, then it's 6 inches from there. That's 12 inches that this gutter or wireway can be at the depth of. So this is a good one to remember, and something again to write down in your Uglies book when you're building these types of installations. There's many cases in residential where a panel will be put behind a door, and it just says here equipment can be located behind the door provided that 3-foot working space can be achieved by closing the door. Again, a lot of this is straightforward. When we look at the working space depth, here's a nice cube that's been given for us to see the depth of 36 inches, and we're going to be a width of 30 inches. The biggest problem in commercial areas is they put stuff right in front of these panels. So a lot of companies have put down on the ground, marked it with like yellow tape, and say no storage. But we still end up inevitably finding things in front of panels. So these depths again and dedicated working spaces are important. This dedicated working space allows us to run conduit out of that panel. So we don't want to put anything else in the way. So quickly touch on what are panel boards, and the panel board in this case would be a main breaker or a main lug. In this one, there's no breaker at the top; it's just lugged in. And so a panel board includes overcurrent protective devices. It includes busing, and is usually mounted inside of an enclosure. When we look over here at the enclosures, we see there's different types. We have a NEMA Type 1 inside only enclosure, and we have a NEMA 3R rain tight enclosure here. So you see the doors will open differently. They open from the top with a drip edge here to ensure that when it rains, there's no water that gets into it when it's closed. Unused openings need to be protected by putting in a filler plate. This should go without any explanation on why you need to do it, because you have energized bus bar behind it, and you could easily stick your fingers in there and end up getting hurt or killed. So they have to be blocked off. It is a code requirement. Circuit breakers. So circuit breakers come in these standard sizes. This comes from 240.6a. And it says here that the standard ampere rating of a fuse or inverse time circuit breakers are 15 amp, 20 amp, 25, 30, 35, 40, and so on. And it continues on here. We need to know this because this is what the manufacturers make those breakers in. Now, when we go to your project towards the end and you need to size your circuit breakers, you need to come back to 240.6 to see what's my circuit breaker size. Let's say that you sized it at 32 amps. It needs 32 amps to run your equipment. Well, you can go for a 35 amp breaker. That's going to be the next closest, but that would be a special order. And maybe need to go up to a 40 amp breaker because you can get those easily. So any of these breakers on the 5s, 25, 35, 45, are all going to be special order breakers. But what's accessible on the shelf, 15, 20, 30, 40, 50, 60, sometimes 70s and 80s aren't available, 90s, and it goes to 100. When we look at a circuit breaker, we see that a circuit breaker with an inverse time is a qualifying term indicating that an intentional delay in the trip action of the breaker. So this inverse time delay means that it will take an overcurrent for a period of time before it opens. It's not instantaneous. So we want to have an inverse time delay when we're starting a motor. We don't want the breaker to trip when the motor is being started and the high inrush current at the very beginning. Common trip and single pole breakers. So the difference between a common trip, when we have two breakers that are put together, they should have a tab between them or a metal bar around them that will, if one side trips, the other side will open as well. So they both will operate together. In this case, this manufacturer has one throw but internally it's a 2-pole breaker and it has a common trip internally. I have seen all kinds of variations here where they've stuck a nail through a paper clip and they don't work because one side will trip and the other side will remain on and burn the equipment up or be unsafe. So it has to be a factory installed common throw device and they need to be put in. They used to have circuit breakers that were stackables and you could put them together and then add these devices in. They've gone away from that. It's hard to find those anymore. And the newer ones are all factory made to be common throws. There may be a situation where you have a 2-pole or a 3-pole equipment, and you have a single pole control power that you want to trip at the same time. And so you might have a breaker that has up to four connected on the pole there. There is a circuit breaker in some of the residential panels that has 4 circuit breakers together, and it's a 200 amp service main breaker. So it's got 2 100 amp breakers put together, but they're installed in such a way that it provides a 200 amp. But it looks like 4 breakers installed under one common throw, but it's a 200 amp breaker in order to give it its 200 amp rating. That's just the way one manufacturer does it. On fuses, we can see that there's different types of fuses here. We have a non-current limiting. This is a knife style cartridge. This is a cartridge style fuse that will just plug in. And what we do know is that a 30 amp disconnect that has fuses in it will not take. It rejects 60 amp fuses because 60 amp fuses are longer than a 30 amp fuse. So this is a good thing that we don't oversize the fuse and then end up causing a failure with the equipment. So you can go 30 amp, 60 amp, 100 amp, and then 200 amp. So the fuses correlate with that size. So if you need to go from a 30 to a 60, then you need to actually change the whole fusible disconnect enclosure and then get the new fuses to go in. For current limiting, we see a rejection style construction to it. It has this lip at the bottom, and over here we have a rejection style blade where there would be a bar across here that you can't put this fuse into this type of fuse holder. So you have to look at what type of fuse you're using in order to get the right one. Screw-in fuses do exist, but I would strongly suggest moving away from that. If you have a customer that has screw-in fuses, it would be a good idea to recommend changing these out to a circuit breaker construction. Also, when you're looking at these, sometimes they took a penny and they put a penny in the bottom of the base and they screwed the fuse back in, and it's effectively bypassed the fuse and it made it non-fused. So that was a safety issue. And you could probably even unscrew them and find those pennies in there as an example that the fuses aren't working. Okay, let's look at the electrical service requirements. I'll be showing you specific pages in the Edison's ESR requirement, the electric service requirement, to correlate back with what we just looked at from the National Electrical Code to show you that there are some very much similarities and there are some more stringent requirements also required here. And so we look here at figure 2 in ESR2, figure 2-6 service drop clearances. This document, by the way, is accessible on Edison's website. So for services 0 to 600 volts, this is the minimum clearance applied to the lowest point of service drop sag. So it's worded a little differently, but we will have a sag from the service point to the pole, and it's from that lowest point of the sag is where we're going to take the measurement for the ESR. So we can see that there's from the point of attachment there should be 10 feet, same as the code. We have 12 foot for private driveways, and then we have 16 feet, and so the 16 foot is at the curb edge of the residence, so right at the street location. And then 12 foot off of the curb and 18 feet up is the minimum clearances for vehicular traffic underneath of that service drop if it's going over a roadway. We can see that the clearances are the same as the code here. We have 36 inches around a window. However, the code said that it was 36 inches from the top of the window down. But here in the ESR requirements, they are going beyond that, and they're saying 36 inches all the way around a window. This is why it's important to know what the electrical service requirements are for the utility you're connecting to, that you can install it per their requirements. This goes above what the code specifies. Now in figure 2-8 is the minimum clearance for service drops of commercial industrial. We can see that the distance is higher here. And we see that in note 1 at 12 foot, the service wire can be 10 feet over walkways if conductor is insulated triplex. So it has to be insulated triplex in order for it to be at 10 foot, but the specifications for commercial service drops is going to be 12 foot here if it does not meet that insulated requirement. We can see that we're accessible by pedestrians in these areas. We have over a private driveway, we're 16 feet for commercial, and then at the curb edge is 16 foot, and then 12 foot off to 18 feet up is going to be the minimum in the roadway. You can see a couple different configurations of this. So the this size of this riser may be governed by the utility, how high this goes in order to make that minimum service drop sag. Now in ESR 5, there's a few illustrations here that I wanted to make sure that you knew about. They don't come out for some reason in ESR 2, but they're very important standards to understand. So there's a lot on here. And in new service installations, that's what we need to make sure you understand. This is for new service installations. There is a requirement that the lowest point of the meter to center of the meter is 4 foot, and the maximum height is 6'3" to center of meter. So this is important, again, specific to the utility. But the idea is that this meter can be spotted or read easily. So now if you put the bottom of the breaker or the highest breaker at 6'3" and the meters above that, the utility could tell you to lower it down because this is their requirement here. And this specifically is talking about separation from gas services and telco and cable TV. And so there needs to be a minimum from center of the telco, cable TV, boxes to the edge is 18 inches, and then from plumbing fixtures it would be 18 inches right here, plumbing fixtures, and then 36 inches from the edge to gas. And so if you would see, then you would have a 30-inch plus working area around here that you wouldn't be leaning up against the gas meter working on the power. So these are the illustrations of the same layout, just on different flip sides of this. And typically gas is going to be put on the same side as the electrical service. Figure 5-5 is the surface mounted or semi-flush meter installation. And this is giving us the working clearance. So here they're calling for 36 inches by 36 inches of level working and standing space in front of a panel. So if there's just dirt there at this point, then this has to be based upon, the meter has to be based upon finished grade and making sure that this working space is level in front of the panel and cleared. Minimum of 10 inches from windows and minimum of 10 inches from the corner if this is on the inside corner. And again, we're at 6'3" is our maximum center of meter height. So I'll just scroll through here real quick. I'm going to show you the different configurations of multiple services. And the other very important part of electrical panels that you need to know is what's called UCIRC right here, this UCIRC number. When you order a panel, it needs to comply with the UCIRC numbers provided here in the ESR. They will only accept these UCIRCs. Primarily, it's giving you not only the panel configuration inside, but it's also giving you the meter clips. So when the meter is stabbed into place, it actually connects properly. So again, different UCIRC number 305. This is reference only. They're not accepting that 339 anymore. Here's a 313, UCIRC number 313. And each one of these is for specific locations, underground service 400 amps. So I wanted you to be aware of this so that if you had to find a panel and be able to install it, that you're doing it properly and you have it all set up and laid out. Always contact service planning of the utility you're working with before you do any work to make sure that the meters spot correctly and that you have the right panel and you have the plans drawn up, because you will also need to get a permit, and the utility will not connect without a permit and an inspection. The inspection has to be completed before the power is turned on. So if you're doing a service change, you got to think about that. You have to coordinate all of it. So a combination meter service here on figure 518 for an overhead dwelling. And this is showing you how the neutral is connected into a lug, and then it's terminated on the bus bar for the neutral. And what is typically done is there's a lug, and then there's solid bus bar connecting the neutral together. So that is done in the panel itself in a combination service. These are more for commercial installations, and this is just explaining how the grounding is done. Here's a three-phase panel, three-phase delta service, likely feeding a pump or a well. And we can see that it's the same configuration here of having that grounded conductor brought in and terminated to the grounding electrode system of the building. And they show here the Article 250 requirements for that. So again, this is the electrical service requirements for Southern California Edison. Hopefully this gives you just a little bit of an overview, and you can see that the utilities will ask for more. Let's go ahead and go back to the book, Unit 9 on grounding. The way this book is laid out is it's sprinkling in grounding Article 250 into the sections that we're talking about. And it's good that it does this because it's going to help you get accustomed to how grounding is done at a residential, at a commercial level, industrial level. And what I'm going to point out here are very similar grounding requirements that are going to be done at all locations of the electrical system. So let's take a look at them. I really highly recommend you go through this and get a good working understanding of grounding. So when we talk about the main bonding jumper, so there's terms here that you need to learn, and we will go over those again later on in the grounding section that we'll talk about. But the main bonding jumper, what this main bonding jumper does is it establishes a connection between the neutral bus and the panel backboard, and the panel backboard then is grounded to earth by the grounding electrode system. And that bonding jumper is used to make the neutral the same potential as the ground or earth. And the reason for that is that when you have a service location or you've established a new neutral from a separately derived system, we'll talk about that later, that you need to make sure that fault current going through the earth can come back to the neutral bus, and from the neutral bus it goes to the transformer and then back through the windings to increase the current on the hot to trip the breaker. So there's a loop that has to occur. And if this bonding jumper is missing, then it has a very, very high impedance path to be able to trip the breaker. There's a couple options. One is using a screw. It's a green screw. and the other is a strap style, and this is set up in a way that you would kind of bend it into place. So you will only install the main bonding jumper at the service location, not installed at any panels downstream of the service, the main service. If you do, you will actually introduce neutral current into the grounding system, and it'll take multiple paths back. So we don't want to do that. If you're putting in a sub panel, the sub panel comes with a green screw, just take it and throw it away. Here's a picture of that. Remote panel boards or sub panels. We see that that is removed and the neutral now is insulated off of the metal backboard, and the grounding bus bar is installed now. Grounding bus bar is attached right to the back of the panel, and the insulated bus is raised off of plastic stanchions and keeps the neutral isolated. So this is very important. Again, all of these code sections are in here that you will need to look at. The grounding electrode conductor connections. So we need to make sure that our grounding electrode conductor is connected to, per the Article 250, it's sized properly, and it's using the proper connections. So, for example, splicing a grounding electrode conductor with a non-reversible crimp splicing, that is the only way you can connect two together. You cannot use a mechanical bolt connection like this here. Or you can use exothermic welding process, which actually welds the two pieces together. A little bit more expensive to do that for residential, but in commercial you would use exothermic welding techniques to connect copper wire to a copper bus bar, a copper ground rod, or to rebar that's going to be encased in concrete. So we need to make sure that we're looking at the right sizing here. So the sizing for grounding electrode conductors is going to come from table 25066. 25066. That'll be an important table to note down and be able to use. Methods of bonding at the service can be threaded hubs. We would need to put in ground bushings here. So these types of ground bushings are available. This wedge bushing is a good option if you've already pulled the wire and landed it and you need to put it in. You can work this around the conductor and you can land it onto the termination. Whenever you have concentric knockouts or eccentric knockouts, you need to put in ground bushings to make sure that the raceway is properly bonded and grounded. These concentric and eccentric type of fittings, they can move and they can break open, and they just have a couple tabs holding them in place, so they're not good ground connections. So bonding at the service, we first will be bonding the connection that is establish electrical continuity. So we need to make sure that we want electrical continuity between all of this. It's one way to look at grounding, is you need to have a good solid path for fault current to return back to the main to be able to trip the breaker. So our bonding, you would read in here in the code that you're not required to pull a ground conductor into a metal conduit. You can use the metal conduit as the grounding path, but I never did that, because the conduit can separate, the fittings can break, and then you lose your ground path. It's one extra wire to pull in. Don't fight it, just put it in, because it will give you the best path back to the service for tripping the breaker. So all conductive parts need to be bonded to make sure that it's all connected together. Now the grounding electrode system. The grounding electrodes are covered in 250.52. They include metal underground water pipe if in direct contact with earth. So I've got to say that caveat right there. If metal underground water pipe is wrapped in plastic or a insulated type piping for corrosion, and then it is not in direct contact with the earth. So this gets knocked off. If it's PVC feeding the house, then you don't have metal underground water pipe. This is going away. You have metal in-ground support structure, concrete encased electrode. So this is rebar encased in the encasing rebar in concrete using the concrete foundation or slab as the grounding electrode. This is the best, the lowest resistance. It gets better with age, where all the other ground rods, grounding connections age and start to fail. Concrete encased electrode is the best way, and it's actually the cheapest way because rebar is already being installed, so you just have to connect to it. Sometimes a ground ring is required to go around the building. In some applications, you'd be putting a ground ring in for high frequency and commercial. You could use multiple different types of grounding too. A rod and pipe electrodes, so ground rods can be installed, but the resistance of a ground rod is much higher than concrete encased electrode, and there could be situations where you need to have the lowest resistance possible because your ground earth that you are connected to is very high resistance. So we have to make sure that when these are being installed, we are connecting properly so the metal frame of the structure can be bonded to, and we can connect the metal structure to the grounding electrode system and then use the metal structure of the building to be our grounding, part of our grounding electrode system, our GES. 20 feet of number 4 AWG minimum bare copper can be laid into concrete, or using half-inch reinforced steel can be done. So I've actually installed the copper wire 20 feet and then connected it to the rebar, and then you have all of that to your benefit. Now, when working with metal pipe electrodes, there needs to be a minimum of 10 feet of contact with the earth. And again, it needs to be bare. It cannot be covered. If it's covered, it does no good because it has no earth contact. Now, the connection to the water pipe, which either needs to be bonded, even if it's not going to be used as a grounding electrode, it still has to be bonded. And it says here, interior water piping that is electrically continuous with the metal underground water pipe electrode, and is located not more than 5 feet from the point of entrance into the building, shall be permitted to extend the connection to the electrode. So within 5 feet of the entrance into the building, minimum or the maximum, you need to make a connection to the grounding electrode system through the grounding electrode conductor. So this 5 foot is very important. The reason is because after 5 feet is where you could get somebody cutting it and putting in a dielectric union, which then opens up the connection. Jumpering a water meter, because the water meter cannot be used as part of the grounding system. So in locations where they're using plastic water meters, you still need to put a bypass jumper across, even if it's metal. But the plastic for sure, because it inhibits that. The other reason for this is when the water company comes out and they are needing to remove and work on that water meter, then they don't want to pull an arc because current is now traveling across this pipe because it's connected to other services that have neutral current on them. So there can be a balancing current of 1 to 2 amps going across the water system when you're looking at the aggregate of current flow across from house to house. So when they open up this, they don't want to get current across there. Or if the utility has an open neutral connection somewhere, then one of these services is going to carry more current. So this bypass jumper is necessary. Rod and plate electrodes and pipe electrodes. Now there's different ways it can be installed here, and we can see right down here at the bottom that we can go 8 foot. So this doesn't mean drive an 8 foot ground rod and leave 2 inches above the ground. It means it's got to be a full 8 foot depth. So the connections are actually intended to be buried. So you need to be fully 8 foot straight down. You can go 8 foot at a 45-degree angle if you're hitting rock bottom. Have that happen. Or you can lay it 8 foot in an 8 foot trench, 2 foot down, 2.5 foot down on a rock if there's rock bottom there. So it's giving us options. Now we can do 2 electrodes And they're going to need to be spaced 6 feet minimum of 6 feet apart. The reason this needs to be 6 feet apart is because you can get circulating current that actually circulates through here because of the resistance of the earth. If you put two rods in right next to each other, they do no good. And we want to make sure that we have enough ground impedance between the two to help this actually enhance it and to meet the requirements of the minimum ohmic value. And we see here that D says that in accordance with 250.534, A2, if a single rod or pipe or plate is installed, it must be supplemented by an additional electrode. But if the single rod or pipe or electrode has a total earth resistance of 25 ohms or less, the supplemental rod is not required. So it's saying that if one of these can be 25 ohms or less, then you don't need it. Need the second one. But you need the second one in order to make sure you have that minimum 25 ohms or less. 25 ohms is a lot. Even if you calculated it out, you would find that there's quite a bit of resistance still there. The grounding electrode conductor, we need to make sure that it is made of copper, aluminum, or copper-clad aluminum, and that it's or other items permitted by 250.68c. Needs to be inhibit corrosion, so it doesn't corrode. I've seen ground rods corroded off in salty areas, where stainless steel should have been installed, and they had no grounding system because that ground rod had corroded off. Proper UL rated and listed connections need to be used to make connections for the grounding electrode conductor. This acorn style connection it works in some cases, and in some jurisdictions they won't even allow this, and you have to use exothermic welding to the ground rod in order to make that good solid connection. But whatever you use has to be listed for the purpose. Establishing the grounding electrode system, you're going to see that everything needs to come and connect to that grounding electrode system. Concrete encasement to metal water pipe, ground rod to the metal water pipe. Now they're using the metal water pipe here as a busing, but ideally you wouldn't do this. Now again, we're talking about dwellings, so this is probably going to be the easiest way to do it. But they do make flat bus bar, and then you would take and drill and tap holes in it, and you would bolt all of these to that connection, and you would do that in commercial and industrial for sure. And here in the service side, we need to make sure that wherever our grounding electrode conductor is, so that is connecting to our grounding electrode. So if water pipe doesn't make direct connection to earth, then it needs to go to the ground rod outside, or it needs to go to the concrete encased electrode first. Then from there it can go and connect to the rest of this. But the concrete encased electrode would typically be a rebar that comes up and inside the wall. This is a brick building, but it would come up inside the wall. And then you would take all of your other connections to that piece of rebar and make those connections to the concrete encased electrode. It's also important that intersystem bonding be completed. And intersystem bonding is where all of the other utilities coming to the house, such as phone, cable, are going to be connected to the panel, so that if the lightning strikes or if there's voltage that's in the system, it would be able to be shunted off to ground through the intersystem bonding connection. Okay, to prevent objectionable current, I'm glad the code does talk about this, because objectionable current is not something we want to have in our electrical system. It will damage equipment, especially sensitive equipment. And it says normally non-current carrying electrical conductive materials are likely to become energized because being contacted together and to the electrical source supply in a manner that is establishing effective ground fault current path. Temporary currents resulting from abnormal conditions such as ground faults are not classified as objectionable current. for the purpose of this section. Objectionable current is current flowing. So, for example, you've put in multiple neutral to ground bonds. You've bonded it here in this enclosure, and you bonded it in this enclosure, and now you can have current flowing across parallel paths, and you could have it going across the metal of the enclosure, and that is not where we want it to flow to. So we want to make sure that we are bonded only to neutral at the service or at the service disconnecting location. So that was a very fast run through of grounding. But again, this is going to be sprinkled throughout. I will repeat myself on this because grounding is typically one of the biggest concerns by inspectors when they're doing inspections on buildings. So I want to make sure you come away from this with a good solid grounding understanding and how it applies and the problems that it might cause. So I hope this helped you out. Unit 9, Services and Electrical Equipment. Please, again, go through the book, read it, and I hope this lecture helped you out. Thanks. We'll talk to you soon.